Welcome to everybody that's online. Mike and I gave this presentation originally in April at a workshop in Dallas, Texas. And so all the material from that workshop is available online. And Barbara suggested that if you have comments or suggestions for improvement of this webinar, to please send her an email. And so, please do that at the end, at the end of today. We are going to have some poll questions, as we noted. It looks like everybody's got the sound is okay, but we're going to try to keep you on your toes. And we have at least 4 more poll questions throughout the time period. So we'll be keeping track to see how many of you are checking in on that poll. And also, hopefully, you should have all gotten an email with all the presentations. And if you didn't, they're posted on APTI, so you should be able to find them. And on the next slide, I will show you where that is. But let me start first with, my name is Hillary Hafner, and I'm with Sonoma Technology. And I've actually been here a long time, over 20 years. I've been working with EPA quite a bit for the last 2 decades, and specifically on air toxics for the last several years. And so it's my pleasure to be working on this project. Mike, you want to say something about yourself?
Sure. My name is Michael McCarthy. I've been with Sonoma Technology for about 7.5 years, and I've been working in air toxics the entire time I've been at APTI, and I'm very excited about today's webinar, and I hope that you guys will all be as excited as I am. So this is our practice quick poll, by the way. I just launched this to see how people are paying attention and to see exactly how many people care. And currently, only 72% of you have voted, so if you want to vote, you've got to vote now.
It's like American Idol.
Indeed. All right, time's up. There we go. Okay. I'm going to show everybody the results. We're excited. That's great. Only 25% of you are not necessarily going to start out excited. So that's good. I'm glad that I'm glad that many of you are excited or very excited to be here. That's great.
Awesome. All right. Well, we'll thank you for paying attention there. We're going to keep you on your toes, hopefully, today. So what I'm going to start with is an agenda, and the agenda is basically mapping out the next, this week and the next 3 weeks. So today we're talking about 2 of the topics from our workshop that we gave. The first topic is going to be an overview of how you make a successful air toxics monitoring project, and then we'll talk about getting started, the sort of initial things that you need to do to get those projects rolling. Next Wednesday, we'll be talking about monitoring strategy and design. It's the real meat of this topic. We'll spend a lot of time on that because it's really, the guts of what you need to know. And then on September 7th, oh, I forgot to take out the minutes there. We'll be talking about collecting and QCing your data, and then also spending quite a bit of time on data analysis and interpretation, which is near and dear to my and Mike's hearts because we're both data analysts, so we really like that part too. And then we'll wrap up on September 14th with a summary, and Mike McCarthy is going to walk through examples of everything that we've talked about up till then. And if you've downloaded all the material, you'll see that we're skipping one section, and that is on communicating and getting community involvement. But I'm going to cover a little bit of that today. So we hopefully will have covered everything, but then you have all those materials and those resources for you, and I've given you the link on this slide. All right, so let's get going. So there's a lot of things that go into making a project successful, and what we've done is we've gone and we've looked at all the, many of the different projects that have been conducted by some of you that are on this call, and also many other researchers out there in the states and local agencies. And we've looked at their reports and their plans, and we've talked to them, and we've also been involved in many of those kinds of plans and projects ourselves. So we tried to build on this collective community of information to try to give you some tips and tricks to help you do a great job when you dive in and take on a project like this. And so we sort of sat back and said, well, what do you really need to think about to make a project successful? What does that mean? How do you define success? So, obviously, to me, it seemed that a project's goals, if the project's goals were met, then you were successful. And to do that, usually you have to have something that's well thought out. You need to be thoroughly planned, and then we're going to emphasize communication and how important communication is during the entire process of the planning, conducting, and then analyzing the data from your study. And you'll see at the bottom of this, of many of these slides, a sort of thought process that we're going to be walking through over the next 4 weeks. And essentially, we're going to talk about each of these topics. And it's hard to see on the screen, but surrounding this is a box. And essentially, if you think about communication is going to flow through this entire process. We're going to be communicating, throughout the process from one step to the next, kind of, skipping back another couple of steps because we have to reassess. So there's a lot of communication that goes on. The project, if the project also can be defined as successful because you hopefully ended in some sort of action that could be used to reduce the pollution or exposure that you set out to try to understand better. And to do that, we're going to talk a little bit about how to engage your stakeholders early and also think from the beginning about what you want as an outcome. What kind of strategy, mitigation strategies are you going to build into your plan? And so you really have to think through the whole process before you even start. So, this is going to be essentially walking through a lot of the lessons learned from various projects, and we're going to use a few projects as examples. Sure. All right. So a little bit more on what makes a successful project. Other characteristics that we see. Did I skip one? I did. Thank you. Sorry, a little technical difficulty here. So we want to make sure that, often what we're doing is trying to characterize the local air toxics issues. But what we found in looking at lots of data is that some of the issues are the same, but some are different from national scale issues. And that's certainly why we want to dive in and look at community scale assessments, because not everything is going to pertain to your specific community. But I think we've also seen that often there are things that we should have expected going in that would probably be similar, and maybe we needed to emphasize other things, and we'll see that in some of the results that we talk about. And I've heard this when we did the workshop and also in talking with other people, communicating results and getting that information out to all the team members throughout all the phases really helped make the processes go better. Or if they hadn't done that, they wished they had. And we heard that from several people at the workshop. Communication was particularly difficult. And we spent some time talking about, the difficulties of talking to sort of antagonistic folks that don't want you to be doing what you're doing or don't feel you're doing enough. And so we did spend some time on that. And I know, and we'll try to touch on some of those aspects. But I want to emphasize again that all the steps that we show here are very important. This process is multi-steps. All right, so let's start again thinking about what makes this project successful. There's many characteristics that seem to be popping up across these successful projects. Again, planning early and then reassessing those plans as you walk through them, because you may be, as you start, you may be finding out, let's say, for example, I'm going to be measuring a specific air toxic, and I find out early in my process that those measurements are not going very well. I'm not getting a low enough detection limit, or I'm having instrument problems. You need to not just keep going. You need to have looked at the data earlier enough that you can now make a change. And one of the things that we hear, if you work with software engineers, is you hear a term called agile. And essentially, they work in short bursts. They plan out a week or two of work, and then they reassess where they are at the end of that week or two, and then they plan the next week or two. And it's called an agile process. And I think about that and how we can adapt that to some of the things that we're doing as scientists and monitoring experts. And I think we can learn from that process. I think that there's a lot of things that we can do along that line. So, you need to really look at your data quickly as you're collecting it, and then adjust your plans and then being flexible. Again, that's that agile process. The other thing is that you need to make sure that you're collecting the data that you need to answer your questions and meet your goals. And that may seem very obvious, but it's interesting how often there's been some projects where they just weren't quite getting the information that they really needed. And so we want to learn, again, from the mistakes that have maybe been made in the past. And we'll talk about how this is an iterative process in your design phase, that you may have certain goals, but you may have to readjust them because of a lack of resources or other things that are getting in your way. So I'm gonna kind of jump in a little bit to a refresher on air toxics, and so Mike McCarthy and I did a.
Hillary,
go ahead.
Hold on one second. I think this would be a good time to launch that poll.
Okay, let's launch the poll. Thank you.
All right, everybody. So here comes a poll, and there is no correct answer here because all of these steps are important, but I'm just interested in finding out what people think are the most important. What of these steps is the most important to you in terms of making a community-scale monitoring project successful? Because that's, we'll try to focus more on what you think are the most important things in terms of what we're talking about over the next few weeks.
Ooh, this is really dynamic for us. I like to see what's happening. We get to see the horse race going on here.
Indeed. So we'll hold open the poll for 1 minute.
Yes.
And then after that, we're going to ask another poll to see if anybody's having any problems with the webinar.
This is good. Good idea. Thank you, Mike, for interjecting.
Yeah. I just think it's a good step. Yeah.
Yeah. While we're waiting for the poll to finish, Mike and I also did a workshop and a series of webinars a couple of years ago on air toxics data analysis. Very comprehensive, very thick workbook full of all kinds of ways to look at your data validation, data analysis techniques, data interpretation. So that's a resource that's very, I think, very useful for you. And this webinar and this workshop that we're conducting has a different tack. We're using that as a basis, and that information's out there. But we're really stepping back and saying, what's the strategy to pull this all together? How do we set this up? So that's what we're trying to do here. So Mike, you're going to close the poll, and
yes.
And
can people see the? Yeah.
All right. So setting project goals. So good. That's one of the focuses of today. So we'll hopefully we hit on that. And I would anticipate we might want to ask this question each time, Mike.
Okay. Interesting.
Good. All right. So let's do a quick refresher on air toxics. And essentially, hopefully everybody online knows that what air toxics are, and they're also called HAPs, or hazardous air pollutants. We're going to use air toxics most of the time, at least that's how I talk about them. And essentially, these are pollutants that are known or suspected to cause cancer or other serious health effects. And there's been a lot of work by EPA and the state, local, tribal governments to reduce the release of air toxics into our environment. And it's certainly been succeeding. We'll talk some about trends later on, but most of these pollutants have been coming down over time. It's a good success story. We're actually really affecting a change in our environment, and that's pretty exciting. There's lots of different health effects. I think most of the time we think about cancer as being one of the outcomes from an air toxic, but there's also all kinds of other damage that can be done from these pollutants. They can be pretty nasty at high I'm using my hand, sorry, at relatively high concentrations. So, one of the things is that the reason why this is important is we'll think in terms of there's acute effects, meaning that that can affect you in a short time period. There's also chronic or long-term health effects, and you can imagine that for some of these air toxics, at acute levels, that would be typically higher concentrations, that we might be looking at screening out data on a 24-hour basis or a short-term basis, as opposed to chronic or long-term, sort of lifelong health effects. Those concentrations that could affect you over a long period of time may be very low. So we're trying to look at this range of concentrations and really thinking both in terms of high values at acute level and annual mean concentrations for looking at chronic levels. So we're we're exposed to air toxics in many different ways, but we're primarily focusing on what we're breathing through contaminated air. But you can also be exposed to air toxics, by eating, drinking, ingesting soil. Hopefully that's just children and not the adults here on the line. Touching, through your skin, and then also through these different ways of contacting air toxics, then you can get accumulation in your body, or you can be ingesting things that have accumulated air toxics as well. I see that there's a question here about whether our presentations from the data analysis seminar are available for download. Yes, they are, and they're all in the, believe in about the same place that you can find this material from this webinar as well. And if you have trouble finding it on AMTIC, you can send either Barbara Driscoll or I an email, and we will point you to it. But it is on AMTIC. Okay, so health effects from air toxics. Essentially, what we're looking at here are, health risks. We're trying to look at health risks, and that's a measure of the chance that you might experience health problems. And essentially, risk is equal to your exposure times the hazard. And it's really just a probability that you might get sick from the exposure to that substance. And essentially, what we're typically doing is comparing ambient air concentrations of these toxics to chronic exposure risk or some other screening level that has been used for acute screening, for example. And these levels have been derived from scientific assessments that have been conducted by EPA and other environmental agencies. And indeed, some of the states will have different values. So there's a range of values you can find out there to compare your air toxic concentrations to, and we'll talk about that a little bit when we talk about data interpretation. So some of the sources of air toxics, again, hopefully you'll know what these are, but thinking in terms of how you talk about them from an emission inventory perspective, we think about major sources and the industrial sources like chemical plants, steel mills, and refineries, and hazardous waste incinerators, and essentially in an inventory, those are the kinds of facilities that are specified by a location in an inventory. In contrast to an area source, which is basically made up of lots of smaller sources such as dry cleaners or gasoline stations, those would be referred to in an emission inventory in some other way. They're basically going to be allocated, their emissions are going to be distributed in an inventory across some other surrogate like population density or something like that. For mobile sources, we're talking about highway vehicles, mobile sources, cars, trains, trucks, marine vessels, etc. And then, there's also the on-road non-road equipment would be construction equipment. And then there's some natural sources, but we're going to focus on the man-made sources of air toxics because that's where we have more control. So just to show you sort of a visualization of what some of these pollutants are, there's some of all the organic compounds, including naphthalene, and those come from different kinds of combustion. You have the heavy metals from metal processing operations, for example, breakware and other things. Perchloroethylene is a dry cleaning fluid that's used. Methylene chloride is used as a solvent. Benzene's in gasoline. Those are just a few examples of some of the air toxics. But there's a lot of resources, both on AMTIC under the air toxics section on the sources of these pollutants and a more complete list of them. This is a new slide from the original presentation that we gave in Dallas, and what I did is I took a slide from Chet Wayland from his presentation because I thought it was a really nice summary of a list of some of the critical air toxics that EPA has been dealing with in the most recent past and some of their sources. So this was a really nice summary of a few of the important air toxics that you hear about, and they're just listed here in alphabetical order. But a few that that I just mentioned, benzene. But We've heard a lot about acrolein or acrolein. I'm not sure how, I think I've heard it said several different ways. We've had difficulty in measuring acrolein recently. It's a pretty difficult pollutant to measure accurately. The measurement techniques are developed and can be done, but in the past there's been some problems with it. And then you're familiar with the metals, but then there's other things that we don't measure very well, like coke oven emissions. There is no instrument that you put out to measure coke oven emissions, but you can measure components of it. The same thing with diesel exhaust. We don't necessarily measure diesel exhaust, but we can measure surrogates for it. So you can see that there's some differences, and you can imagine when we start looking at all these different pollutants that there's no one way we're going to measure all of them, and no one way that we can, easily quantify all of these in the study. So there's one of the keys to project design is understanding those emission source type characteristics. That's why I'm sort of hounding on it a little bit right now, is that we need to know what pollutants we're looking at and what possible sources they might be from, because it's going to help us in our study design. And what I mean by that is, for a localized source, like an industrial plant, or a location that we know, a metals processing plant, we know that the emissions of a specific pollutant might be coming from there, and we expect that the concentrations will be, higher closer to that source, and there'll be this sort of steep gradient in concentration away from that source. That concentrations will drop off rapidly away from that source. That would be one of the ways that we might think about, a localized source with, with that a real specific pollutant being emitted. In contrast, if I've got lots of little sources of a pollutant spread around, let's say benzene from gasoline, then I would expect that those emissions and those concentrations are going to be well distributed across that urban area. You're not going to, it's going to be harder to see, an individual source of that pollutant. Mobile source of toxics can be exhibiting both sort of the point source, that localized steep gradient versus area source characteristics, depending on how close you are to the roadway. And there's been a lot of emphasis currently on near road measurements. We're right now focusing on NO2. They've just added carbon monoxide, and the concentrations of those pollutants are certainly much higher at the roadside than they are, a few hundred meters away from the road. And some of the air toxics will probably show similar characteristics. All right, so that is the end of my piece, and I've answered one question, and Mike answered it with a link. Are there any other questions? Anybody want to type in something that we might look at? Otherwise, I'm going to turn it over to Mike, and we can come back to questions at the end of his presentation. So, Mike, if I do this, I want to make sure I give keyboard and mouse.
All right. Well, while you're doing that, I am going to launch another poll. So everybody, please pay attention to your screens.
You have 1 minute to call in. Oh, sorry.
Yes, here we go. Okay. It's a very easy question. All right. Okay. So let me see if I'm able to. Theoretically, I have control now, although I'm not seeing the screen anymore. So at this point, it says that 84% of you have no problems of, well, everybody says they're not having any problems with the webinar, which is good, and 87% of you have voted, so that's good enough for me. All right.
So Mike, can you see the screen?
No one is having any problems. Hooray. Okay.
Oh, good.
Okay, so now let me see if I can actually, if I'm having any problems with the webinar. Okay.
I just saw you change it.
There we go. Okay, so apparently I am not having problems with the webinar either, which is good. My section is basically going to talk about a number of physical and chemical properties of air toxics, and then I'm going to give you sort of a not quite top 10 list of things that that we've learned over the last 6 or 7 years about air toxics and just wanted to sort of put everyone on the same footing in terms of understanding what air toxics, what you might want to think about before designing or trying to answer questions. What is already known about air toxics, just in case you aren't 100% up to speed. And I want to make sure that everyone knows they can ask questions by typing into the little box, and we really like having you ask questions because it gives us something to do, and because it helps us to gauge what the level of understanding is about what we're talking about. If there's no responses at all, then we don't know whether you're paying attention, except for the fact that on the screen that I have here, I can tell who's paying attention to the webinar screen and who's paying attention to something else by this little exclamation point thing. So do know that if you're not paying attention, I can tell, because we have that sort of power from this webinar control interface thing. So I'm taking notes, and if you're not paying attention, then I'm gonna tell on you to somebody. So now that we've gone that, before I go into this, I'm going to launch another poll to see what people know about the things I'm going to talk about. All right, so here's the poll. You have 1 minute to ask the question, and or to answer the question, which of these following statements is true? And I'll go ahead and read them off. Most air toxins are routinely monitored in the U.S. Background levels of carbon tetrachloride are greater than the 1 in a million cancer benchmark. Concentrations of air toxins are increasing over time, or less than 25% of air toxin measurements are less than method detection limits. And because of some character limits, you can't see the whole question some of the time. But which of these statements is true? All right, so we've got about 20 seconds left on the poll, so make sure to get your vote in.
I'm going to do this at meetings here, Mike. This is really fun.
I am enjoying this. All right, so I am going to close the poll. 90% of you have voted. The other 10% have not voted. You're just not willing to guess. That's fine. All right, so I'm going to close it, and I'm going to share the results of what people think. So there's a wide variety of possible answers here, and I am not going to tell you what the right answer is, so you have to pay attention to find out which one of these statements is actually true and which ones are false. So these are all going to be topics that I'm going to be covering in the next half hour. So pay attention, and I will show the poll and give you the right answer after I've talked. So that was the pop quiz. And I don't see any questions at this point to asking what the right answer is. So okay, I'm going to hide that for now, and we'll go back. That was very interesting poll results. I'm excited about this little. I'm going to have to make like 40 poll questions next time. I'm going to ask you questions the entire time. Okay, so air toxics, there's a whole bunch of air toxics. There's 188 listed, and there can be more that are listed, but in the Clean Air Act amendments, 188 are listed, and then there's been like one delisted. And they have a whole bunch of different physical properties because they are anything that can cause harm to human health. And so those include particles and gases and semi-volatile organic compounds, things that are emitted directly into the atmosphere by various sources, or things that are formed in the atmosphere through photochemical reactions. They are mostly from anthropogenic sources, but there are air toxics from biogenic or geogenic sources. So various algae in the sea create chloromethane. Volcanoes can have hydrogen disulfide, that sort of stuff. And there's a question there, and I'm not going to be able to answer that right now while I'm talking, but I'll let Hillary try to take a shot at that a little bit later. And they have a wide range of atmospheric lifetimes, which is important for understanding how long they last and how their gradients change away from an emission source. And then as an additional sort of complication, some air toxics not only are toxic to human health directly, but they indirectly are toxic to human health by forming ozone or PM indirectly through reactions with other compounds. And so this makes them an incredibly complicated range of properties. But we're going to try to give you a few basic things for trying to help to conceptualize what a spatial gradient or a temporal variability or how a pollutant is going to change depending on the physical properties it has. And most of these pollutants, we do know something about their physical properties that we can use to guess how a pollutant is going to behave in the atmosphere. So this is important for your study design for understanding what you should think about. Okay, and I think that okay, I'm trying to move forward, thinking. Hooray! Okay, did it just go forward twice? It did. Can I go back? I hope I can go back. Let's see. No, I'm going forward more. Okay. No. Okay, good. All right. I was using the one button. Okay, what? Okay. Great. So we just caught that. Okay. So this is sort of an example of what Hillary was talking about earlier in a highly conceptualized model form. If you have a facility with a stack that's emitting some air toxic pollutant, the solid black line indicates what the possible gradient of it would look like. So at first, right next to the source, it doesn't look so high, but then it goes up as the stack pollutant plume, mixes down to the ground. So like, at 1,000 meters, you might have the maximum concentration, and then it steeply declines after that because there's one emission source that goes away after it has that maximum impact, and then sort of drifts away very quickly. In contrast, something from an area source where there's multiple small sources of a compound, they might have high concentrations next to an individual source, but it's going to have a shallower gradient because there's overlapping emission source plumes, essentially, that are sort of making up the airshed. And so it's going to have a steeper gradient. So having a conceptual model of how a pollutant concentration is going to change in a line from a source can be a helpful way of designing the right place to put a monitor if you're trying to characterize an emission source. Okay. The other thing that should be noted about this is in the AQS database, most monitors are listed as, it's a near facility source, or it's a regional monitor, or it's a background monitor. It has some sort of monitoring purpose, but that's usually not going to be applicable for the whole range of air toxics. For some air toxics, you might be right next to a facility, but for other air toxics, it might be a background source, depending on where the emission sources of these different pollutants are. So that's an important thing to consider. All right, now let me try going to the next slide. Okay, so thinking about formation, destruction, and transport, if you're not a primary source, if a pollutant is not primary, if it's a secondarily formed pollutant, like ozone for a non-air toxic, or formaldehyde or acetaldehyde for air toxics, secondarily formed pollutants are typically not high right next to their precursor emission sources. They're often higher much further downwind after the plume has aged and been photochemically oxidized. So wherever the precursor compounds are highest, you wouldn't necessarily expect the secondarily formed pollutants to be highest. You'd expect them to be higher further downwind. And as a result of that, and because the photochemical oxidation process takes time, they tend to not have very steep gradients in concentration over space. And so you can usually consider them more regionally distributed than a lot of the primary pollutants. Switching to transport distance, when one is thinking about how long a pollutant is going to last in the atmosphere, one needs to consider what the chemistry of the pollutant is in the atmosphere. So some pollutants are reactive, some are highly reactive, and so they're going to oxidize quickly. Others are non-reactive but may deposit out of the atmosphere through, particles may fall out of the atmosphere or rain out of the atmosphere. So understanding the chemistry, or having an idea of what the chemistry is, will tell you something about how long a pollutant will last. And so the key thing to think about this is that if you have a very short-lived pollutant, it's going to have a steeper gradient in concentration near an emission source than a very long-lived pollutant, because it will, in addition to being diluted, it's also going to be removed very quickly. Whereas if it's not removed very quickly, if it stays in the atmosphere for a long period of time, then it's going to be transported downwind, and this gradient will be less steep. In addition, meteorology is always important for all air pollutants. The higher the wind speed, the quicker pollutants are going to dilute. The higher the mixing height, the larger the amount of atmosphere that a pollutant has to emit into, the more it's going to dilute. Additionally, if you have precipitation, that's going to change how many particles in the air. And then, of course, topography is going to channel your wind flows. And that last bullet is basically thinking about a couple of air toxics, carbon tetrachloride, chloromethane, methylchloroform. All those have very long atmospheric lifetimes of months to years to decades. And when a pollutant lasts that long in the atmosphere, you can stop emitting it, like we've basically stopped emitting carbon tetrachloride for the last 10 years, but it's still going to be in the atmosphere for another 100 because it's basically just not removed. It's sort of just floating around the atmosphere forever. Okay, moving on. Let's see if this will... Okay. All right, so we just kind of talked about this, but I'll go over it. The chemical reaction pathways that remove pollutants are basically a reaction with hydroxyl radical or the nitrate radical or ozone. All of those will remove volatile organic compounds and other reactive compounds from the atmosphere. Photolysis will remove some of them, and that's both of those things are going to be faster in the summer when there's more solar radiation, which drives the photochemistry. And then physical processes, wet or dry deposition, are the key ones that are going to remove pollutants from the atmosphere. Stickier pollutants are going to deposit and stay on the surface more rapidly, and larger particles are typically going to deposit large particles, coarse particles greater than 2.5 microns in diameter. And again, the key point about all this residence time is basically having a conceptual model of what a pollutant is going to do in your community. If you have an emission source of a pollutant, is that pollutant going to go away as soon as it's emitted because it's removed very quickly, or is it going to be transported long distances because it's not removed very quickly? That's the bigger, the best way of thinking about this for designing a project. And over a community scale, depending on the size of the community, if it's 50 kilometers that you're considering monitoring across, then that's a relatively short distance. It's only the pollutants that are really reactive that are going to have these sorts of impacts that are going to matter in terms of the residence time, unless you have something that's being transported from upwind, which is impacting your community, which might be something that you want to know about jurisdictionally so that you can get those upwind folks to stop emitting so much of that pollutant that's impacting your community. Okay. All right, so now I'm going to go into that part. So I've already talked about the residence time. Now I'm going to go into talking about what things you need to know about air toxics. This was going to be a top 10 list, but we ran out of space, and so it's like 7.5 or something. So, and we've talked about the summaries of results that are available from previous air toxics community scale projects and from national projects that are available. There's a website there. So I'm going to talk about what I think are the most important things. If you have it, please ask questions about these because I think these are very important. That's why I'm saying that they're the key things you need to know. First, measuring air toxics is expensive and complicated, especially compared to criteria pollutants. And I've given a number of examples in sort of this bullet form, but the key thing is if you're measuring a criteria pollutant like ozone, you've got a FRM method, which is basically known. You're going to get 8,400 samples from your hourly measurements, whereas with air toxics, you have to choose what type of pollutants you're interested in monitoring. Let's say you go for VOC canisters. Typically, you can only do about 60 samples per year at one site, so you get 60 samples versus 8,400. So that's, you're not getting nearly as much for your money there. The capital costs are a little bit more expensive for air toxics than they are for a criteria pollutant monitor, where you buy the instrument at $15,000 and then you basically let it run. Toxics, you have to get a sampling unit, you have to ship things to the lab, you have to have people go out and get the samplers, that sort of stuff. And then on top of that, you have these recurring annual costs of $20,000 to analyze that pollutant. For if you have 60 samples at $300 a pop, that's $18,000. Whereas for operating for an ozone monitor, you just need some calibration gases and much, much cheaper. Now you do get more species, but then that makes it more expensive, complicated, and time-consuming to quality assure and quality control because you don't know as much about ozone and what it should be, or about air toxics and what they should be doing as you would with ozone. And then all of those things being considered, that's just for one set of pollutant types, like volatile organic compounds. If you also want to get polycyclic aromatic hydrocarbons and metals and carbonyls, you've got to have 4 different methods out there, which quadruples your cost, and you've got all these different labs that are involved. It becomes very, very complicated relative to a criteria pollutant measurement. Okay. So here's the answer to one of the first poll questions. Most air toxics are not monitored routinely in the United States of America. I'm showing a list of the 188 air toxics that are listed in the Clean Air Act. The ones colored blue are the ones that are monitored at more than 20 sites nationally as of 2003 to 2005, although basically the last few years not much has changed in terms of this list. Maybe a few more have been monitored, but not too many more. All of the other pollutants that are listed have less than 20 monitoring sites if they're sort of regular font. If they're italicized, there were no valid annual averages for a pollutant of that name in the air quality system between 2003 and 2005. So more than half the pollutants are not monitored and reported to AQS at all. So even with all of the different monitoring methods we don't monitor most of these pollutants. And some of these may be a problem in your local community, but there may not be a monitoring method that's going to be useful for capturing them on a routine basis. Okay. Here's an indication. Here's a relatively complicated plot, and if you've heard me talk in the last 4 years, you've probably seen this plot. What I'm showing is the risk-weighted concentrations in per million people. So on the x-axis. So what that means is that if you're above the 1 line, which is sort of going up the middle here, then that means that a pollutant listed there has a risk-weighted concentration in the ambient atmosphere at all the sites monitored, or the 10th and 90th percentile of sites nationally monitored that monitor that pollutant have concentrations above the 1 in a million cancer benchmark that was recommended by EPA in 2007 when we made this figure initially. So all those pollutants in the A box are the pollutants that have median concentrations nationally above the level of concern, and that's for annual averages. Now, this is in good agreement, basically, with the list that Hillary showed earlier that Chet Wayland had talked about. A couple of pollutants that aren't on the list are ethylbenzene and formaldehyde, and I'll talk a little bit more about why they may not be on there later. Note that this is just for cancer. Acrolein is a non-cancer hazard, and I'll talk a little bit more about that later. But it's basically the only major pollutant that's a national concern for the non-cancer hazard value. Okay. All right. So this is another relatively complicated plot, but there's 2 key points I want you to get from this. First, the triangles are an estimate of background that we came up with in 2006 as part of a journal article that we wrote. And so the sideways facing triangles are those background concentrations. The crosses in the different colors and shapes and fills indicate different cancer benchmarks for these pollutants. For 3 of these pollutants, those triangles are farther to the right than the crosses. And the key pollutants where that is the case for are carbon tetrachloride, benzene, and formaldehyde for some of the cancer benchmarks. That means that those pollutants, even in the remote northern hemisphere in places like Alaska and Hawaii where there are no measurements, or where there are measurements but there are very few emission sources nearby, the concentrations are higher than the 1 in a million cancer benchmark, indicating it's probably a level of concern. So even in the remotest areas in the northern hemisphere, some pollutants are above levels of concern. So that's important to know when you're considering, interpreting your results. Are my pollutants above levels of concern? Yes, but they're also above levels of concern in the remote Arctic, and therefore, it's not necessarily our fault if we're above the levels of concern, because these things are transported globally and therefore have high enough concentrations to be above levels of concern. The second key point here is that different agencies have different cancer benchmark recommendations. And so it's important for you, if you're not a health person yourself, to know which benchmark to use, and that's going to be something that you're going to want to talk to your health department or your local risk assessor to figure out what's the right benchmark to use, because there are a wide range of values. For some of these pollutants, such as formaldehyde, risk benchmarks can vary by orders of magnitude. For others, they only vary by a factor of 3 or 4. So, but that can be enough to put you above or below a level of concern, and so it's important to understand which one you're using and why you're using it. Okay. Next. Okay. Another key point, and one that we will harp on a lot in the monitoring design section, is that monitoring methods often have method detection limits that are too high to characterize risk. And so you've seen this plot before. I've just made it bigger. Again, this is showing the 1 in a million risk-weighted concentrations. In the box labeled B, which I'm circling now, all of these pollutants have more than 85% of their measurements nationally at levels below the method detection limit. And so our data treatment for these was to just substitute method detection limit divided by 2 and to plot them to see what the possible levels of risk are nationally for these pollutants. And so these pollutants in the B box are ones where the median level concentration for these pollutants as estimated by method detection limit divided by 2 are greater than the 1 in a million cancer benchmark, meaning that the method detection limit is higher than the cancer benchmark or the level of concern, and therefore if the concentration is below that method detection limit, you can't say whether that pollutant is or is not at a level of concern because the method detection limits are too high. In contrast, all the pollutants in the C box on the bottom here have that same treatment, method detection limit divided by 2, because most of their data is below detection, but the method detection limits are low enough typically to say that the concentrations are also below the levels of concern. So as long as your method detection limit is below or close to your level of concern, within a factor of 2 or so, you can say with some certainty that the pollutant is probably not a problem. But if it's too high, then you can't say that, and therefore you can't characterize the risk for those pollutants. Okay.
Hey, Mike?
Yes, Hillary.
I realized that you answered one of the poll questions in a slide or two ago about the background level of carbon tetrachloride being greater than 10 to the minus 6.
Right. Well, I'll go ahead and share the poll results again because I think that we've already covered a few of them.
Okay.
Okay. So that first one, most air toxins are routinely monitored in the USA, is false. The third one, or I guess we found out that the background level of carbon tetrachloride is greater than the 10 million cancer benchmark. And so that one is actually true. And so I'm sort of stealing my own thunder by saying that this is the true one, and 26% of you were correct. And so the other two are false, and we'll talk a little bit more about those two later. Okay. All right. All right. If you don't have any measurements in your local area or you don't know what the pollutant concentration should be, you can go to an air quality model, such as a National Air Toxics Assessment for the year 2005, and get a decent estimate of what the pollutant concentration is going to be for your local area. This plot shows the ratio of model to monitor concentrations at a specific census tract for all the monitoring sites in the U.S. And it shows the median and interquartile range, the 25th to 75th percentile values for concentration nationally. And the yellow band indicates a factor of 2, which is usually considered sort of good agreement for air quality models. And so you can see that for most of the air toxics listed here, which are all VOCs, the concentrations are typically within a factor of 2 of the predicted concentration. The predicted concentrations are within a factor of 2 of the annual average concentrations measured at the site. So that's good. Now, it should be noted that gases are predicted better than metals. So if you don't have any information about what a pollutant concentration should be, then you can use the NATA model to sort of come up with a preliminary estimate of what the concentration is going to be in your local area. All right, so some of you guessed that concentrations of air toxins are increasing over time, but this plot shows that for most air toxins that we measure at multiple sites in the U.S., the concentrations are decreasing over time. And what I'm showing is the percentage change per year in a pollutant concentration. I believe this was from 2003 through 2008. And the X's indicate the median site nationally, and the bars indicate the 10th to 90th percentile trend sites nationally. So if the X is to the left of the 0, then basically you have a decreasing concentration at more than half the sites in the U.S. And so, for example, for the hydrocarbons, for most of the aromatic compounds, you have about a 5% decline on average nationally at more than half the sites. So we're getting a pretty good decline in concentrations over the last 6 years or so. And we've updated this plot with 2010 data, and the trends are more or less the same. Now, some pollutants are not declining as quickly as others, or are right on that zero line, so we'd say that they're not declining. But on average, more pollutants are declining, and almost no pollutants are increasing over time, or they're increasing only a tiny bit. So basically, we are decreasing the concentrations of most well-measured pollutants for air toxics. Okay. All right. So this is sort of a data analysis technique. If you are taking sub-daily measurements of air toxics, you can come up with a conceptual model of what the emission source is and what its activity is. You can identify what the meteorology is happening on a daily basis, and then you can combine those to sort of estimate what the concentration pattern should look like over a day or over the course of a season or a year. So in this example, we're illustrating what traffic activity emissions are in this bottom black line. We're indicating what the dispersion of a pollutant concentration would be based on the inverse mixing height. So the mixing height is how much, what the height of the atmosphere is through which air is well mixed. And so if you have a lot of air to mix into, then your pollutant concentration is going to be lower than if you have a little bit of air to move into. So basically, the inverse mixing height indicates when you have a lot of air to move into. And then solar radiation is shown in the top dashed line, which indicates for some pollutants a sink source. So or a sink, such as OH radical, will be more active during the day. And for other pollutants, OH radical will actually be a source because of secondary production. So for example, formaldehyde. So if you put all three of these together, you might come up with something like this. What I'm showing here is hourly concentrations, I believe is median hourly concentrations nationally of all 1 hour concentrations for like 5 years at TAMS monitoring stations for these 9 pollutants. And you basically see that all of them more or less follow the same trend where there's a sort of peak at 6 or 7 a.m., there's a big decline in the mid-afternoon, and then there's sort of an increase at the end of the day. And if you looked at those 3 plots that I showed you earlier, the dispersion, sort of this big daytime decline is sort of a function of dispersion and removal. The morning peak could correspond to that traffic activity, and sort of the nighttime would be a time when there's a low mixing height, and so there's less dispersion then. And so we could say with some confidence that it's likely that mobile sources are contributing a significant amount of these pollutants in order to be sort of impacting this, causing this morning rush hour peak to appear. And so we could say that we have some confidence that that these pollutants are all being emitted by mobile sources. Okay. So this is sort of the answer to the last poll question. This is taking all of the data that are listed as air toxics in the air in AQS. What fraction of them are reported below method detection limit per year? And so we see that over time, more than 50% of data have been reported below MDL for all years since 2000. And the concentration trends are not, well, not the concentration trends, the method detection limit, the number of data below method detection limit is not declining over time. More data and more data are, well, at least as much data as before is below method detection limit. And that's possibly because the air is cleaner, and it's possibly because our techniques are not sensitive enough. But whenever you're designing an air toxics monitoring study, you need to know that a large fraction of your data are probably going to be below method detection limit if you do not get a sensitive enough technique to measure concentrations at the levels concerned, or at levels that you're interested in your local atmosphere. Okay. Okay, and so I think that we've already covered this. Don't know why. Okay. I'm not at the beginning again. All right, so we're at the end of the slideshow. So I think, Hillary, you're in charge again.
I am. So I think it's time to launch our final question, right?
Sure.
It'll lead into the, okay, hopefully I have the keyboard again. So we're going to go ahead and launch while I load up here.
Do you want me to launch the poll?
Yeah, let's go ahead and launch the poll because it's going to lead us into the next discussion.
Sure.
And thanks everybody out there for hanging in there. I know we always feel like we're certainly downloading a lot of information to everyone that's listening, and I know it's easier in person, so I appreciate all of you for hanging in there as well. So this next section, as we're running the poll here, is that we're going to get started. We're going to start our thought process. We're going to go to the first, establishing a stakeholder group and sort of thinking about how we're going to set goals. So we're running our poll. Good. We've got about half of you have voted. So at least half of you are still awake. Okay. No lunch comas out there. Oh, good. We're getting back up there. That's good. Good to see that most of you are still with us. All right. The poll that we have, I'm going to read it because it's going to be recorded here, is, which of the following project planning steps is most difficult? And there is no wrong or right answer on this one. This is going to be really feedback to us on what you're trying to come up with. And the answers are A, constructively involving stakeholder groups; B, identifying what issues are of concern; C, setting realistic project goals; and D, managing expectations. And I think we're ready to close the poll and share it here. All right, and so there's actually all four of those are important to some of you, and it seems like one of the most important things we're seeing here from this poll is setting realistic project goals, and that is certainly very difficult. I'm going to start, though, with talking about involving stakeholder groups, which also is of importance to many of you out there. So again, thanks for hanging in there, and please send us questions if you've got them. All right, so what we're going to cover in this section, in our remaining, I'm going to try to get done in less than an hour here, is establishing a stakeholder group, identifying issues of concern, setting project goals, and lessons learned in setting project goals, because that is always something we want to build on, is from what other people have learned. So starting here, I would think when I was first putting this together that this may seem early to you. Why are we starting with establishing a stakeholder group first? Shouldn't we be setting our goals or identifying what our issues are of concern? And really what we're trying to do is engage the right people right up front and have everybody involved from the beginning so there's no misunderstandings and that we have a common path that we're trying to share. And certainly in the workshops, there was a lot of talk about how hard this can be. It can be contentious. It can be difficult to find the right people. You need to be careful how big the group gets, because if it's too big of a group, it's too hard to make decisions. So this is a tricky one. And really what you're trying to do is really go to the name of stakeholders. You're trying to identify those folks who hold some kind of stake or have an interest in that project and its outcome. And we want you to make sure that you're including people from your community, from the industry that you're interested in trying to look at if that's part of one of your goals, and your government folks. And then make sure you're discussing that entire process up front. And one of the things that came out a lot was make sure that you understand people's expectations. If we don't know what their expectations are, then we can't figure out how to at least address them. And what we talked about in the workshop, what we got a lot of feedback from, is that this certainly needs a lot of patience. This step needs a lot of patience. It needs a lot of time. It needs lots of discussion, and it needs compromise. And it seems like nowadays compromise is kind of a dirty word. That we're not hearing that in politics these days. So compromise is really important. You're not going to be able to meet everybody's needs, and I think that's something that can be talked about right up front. The other thing that we heard a lot is that you may need an educational component. And what I mean by that is that the people that you've brought to the table here may not understand technically what some of the issues are that you're addressing. They may, they just may need to be brought up to speed a little bit more, and certainly these kinds of webinars and things might be useful, that you could send people off and, hey, you need to learn a little bit more about this process. And then also, I recently went to a communication, it was called Community Involvement Conference. It was run by EPA, and it was primarily set up for Superfund folks. but I took all the risk communication classes I could take, and it was really, really eye-opening. And I think that risk communication training can be really helpful. So I'm going to share a couple of things from that I actually don't even have in the slides, but that's also to keep you on your toes a little bit. So how do we foster community participation? One of the techniques has been to use established community groups. So if you're looking at a concern, there's often a group that has that same concern, and they're going to be ready and probably have some structure available for you to work with. You can also work with your communication groups because there's often outreach folks in your own agency that can help you develop outreach material to reach out to the community. You also need to plan how your results and findings will be shared and what actions might be taken so that, again, that you're not setting up unrealistic expectations throughout your process. And then you want to think about how to deliver news to the community that they may not be expecting to hear. And that came up quite a bit. And again, there's lots of techniques available. And one of the things I wanted to share was on risk communication, and really what I learned from taking all these risk communication classes a few weeks ago was that it's really just communication. It's human communication. It just happens to be that you're talking about risk. But one of the things that came out was when people are stressed and concerned and worried about something, and air toxics certainly cause that, that they want to know that you care before they care what you know. In other words, you need to show that you're going to try to address the situation because you really care about it, and then they'll hopefully listen to you. Folks also, when they're stressed, they have difficulty hearing, understanding, and remembering information, so you have to keep that in mind when you're doing any kind of discussion, and that could be in your stakeholder groups. You have to keep the message short and to the point, and and really listen. And then you also folks they'll seek out credible information, and they'll make quick decisions that are difficult to change. So people come in with a preconceived notion. They're going to come in, they know the right answer, why aren't you doing this? And so you have to realize that that's going to be kind of the communication that you're dealing with. And there's lots of techniques with which to address that, and usually folks take this kind of risk communication training and come out with some of the techniques. But there's some rules that EPA has put out there it's called the 7 Cardinal Rules of Risk Communication, and I think if you Google that, you will find it. But it was basically based on Dr. Vincent Covello, C-O-V-E-L-L-O, and he basically came up with these rules, and he's also, if you Google him, you can find him. And the first rule is that you need to accept and involve the public as a legitimate partner. And typically, as a monitoring agency, we're going out and developing these studies. We may not be thinking about that. And anyway, it's very important to do so. Secondly, is to listen to the audience, or let's say we're in a stakeholder meeting, is to listen to everyone. You really need to make sure that you're hearing what they're saying. The other thing is risk communication. You have to be honest, frank, and open, and that, I think we all try to be that way, but you need to make sure that you're not holding something back. And then it also said make sure you're coordinating and collaborating with other credible sources. So make sure you have the right people in the room. You've got people that know what they're talking about, or at least have the power to say, I don't know that, but I will get back to you, and then follow up. Another rule is to speak clearly and with compassion. I think most of us really care about what we're doing, and that can come across, and it needs to. But you also need to speak in language that the people that you're talking with will hear. And then plan carefully and evaluate the performance of your communication. I skipped one, which is meet the needs of the media, because I don't think usually we're going to be dealing with the media, although I may be wrong on that. Some of you may be doing that. And I would say if you're having to deal with the media, that you need specific training for that, because that's real tricky. I fortunately haven't had to do that. All right, excuse me. So there are techniques on fostering that community participation that we want to build from, and I particularly would think many of the things that we saw at that community involvement conference are probably online as well. And I would recommend going and taking a look at some of the presentation information that was available from that recent conference. All right, So what we're going to do is we're going to talk through a few examples of some projects and the kinds of stakeholders that were involved. And these are projects that SCI has been involved with. And so that's why I'm using them. It's not to pick on them or single them out, but it's really because we were the most knowledgeable about these 4 projects, so we could use them as examples. And what we've done here is we're going to use examples from these 4 projects throughout the rest of the webinars because, again, we can use them. We had the material available, and they're good examples of things that you can do. So we've color-coded them here on this graphic. The projects were a Joint Air Toxics Assessment Project, or JTAP, in the Phoenix area, the Detroit area, Michigan analysis of air toxics data, the US 95 Mobile Source Air Toxics Project, or Nevada Department of Transportation NDOT project in Las Vegas, and the NESPERS analysis of air toxics data in Lewiston. So again, we're going to use these as we go forward. So this is some examples of the kinds of stakeholder groups that were built for each of those projects. And so what we've done is sort of classified them in various areas: federal, state, community and environmental groups, city, county, industrial, tribal, university, and then the red ones correspond back to JTAP, blue was Michigan, yellow or orange was NDOT, and then the green was NESPERS. And you can see that each of these projects had a pretty wide range of stakeholders that they were working with. And so they had to build these groups, talk with all these folks, keep the ball rolling on these projects, and really involving lots of them. So these were good examples of multi-jurisdictional projects, and I think that they all had their ups and downs as far as the communication issues, but they really wanted to keep people involved, and I think all of these had, or at least a couple of these had some public meetings involved as well. So that's what I have so far on building a thinking about building your stakeholder group. I think there's a lot of other information out there, but we at least want to give you an overview of it. So let's go into identifying issues of concern. I know this is one of the things that folks are interested in, but what we're trying to do is first starting out with investigating available information. And as Mike noted earlier, you can use NADA, the National Air Toxics Assessment, helps you understand whether there might be some pollutants in your area that stand out as far as having higher concentrations than expected or than the national norm. And that they essentially give you some risk characterization information down to the census tract level. So those are quite useful. That's a useful place to start. There's also health data, for example, from the Centers for Disease Control, CDC. There's also national and state compilations of information that might be useful. And then it's always useful to go back and look at national emissions inventories, the toxic release inventory, or locally developed inventories if you have such things available. They'll start helping you identify what might be some pollutants that you want to investigate further, et cetera. This is just an example of the kind of output that you can get from NADA. They've got it's a useful prioritization tool. It helps you look at geographic areas related to other parts of the country. This is just a map showing the areas that have cancer risk greater than 100 in a million based on all the pollutants and listed, that NADA investigated. And then you could dive into the emission sources that are driving those higher risk, cancer risk categories in these different areas. So it's very useful information. So other ways to look at issues of concern to your community might be to look at the emission sources in your area.
Hillary, I'm not seeing the slide change on the webinar.
The slide?
Anyone else have? Yeah, at least on mine, it's still on identifying issues of concern.
Oh, it doesn't say, it didn't change? Huh.
Is anyone else having that problem?
Interesting. So mine, I now says issues of concern to your community. You don't see that?
I haven't seen the NADA map or anything else. I'm not sure.
Oh, it just sort of
there we go.
solved?
Now it's at NADA map. Okay, never mind. Now it's there.
So it's just slow, but I'm on issues of concern to your community now?
Yes.
Slide 8?
Okay. Maybe I don't know if that was just me or if that was just a slow internet connection or something.
No,
All right,
it was like that for me too, also, actually.
It slowed down for you too?
Yeah, so now it's on issues of concern to your community.
Okay, great. Oh, so something must have slowed down. I apologize. There was a network issue. Okay, looks like we're good now. I'm seeing
Can you go back to the map just so people can see it?
Sure. Here's the map. Okay, so it sounds like it slowed down for everybody. I apologize for that out there, guys. We must have had too many downloads going on here at STI. Okay, so hopefully you can all see the map. This is a NADA output that's really useful to sort of compare your area with other parts of the country and to help you identify and drill into to pollutants that may or may not be of concern, higher concern in your area. The database is quite rich and full and useful, and it's readily available to you through EPA. Okay, now I'm going to go ahead. So what we want to look at is issues of concern to your community, and some other places to start in addition to NADA is the emission sources in your area. For example, you might have a school that's located close to lots of industry. So this is an example of a Google map showing lots of industry around a monitoring site, and that monitoring site might be a school or a park or a hospital or something, and we might want to go in and see, looking at this map, it looks like there might be impacts from local industry on this location, so that might be a place to look at. We also we might want to look at what pollutants are of particular interest. Again, that could have been from NADA, it could be from your emission inventory. We want to consider pollution transport. So again, if you look at this picture, it's great. It shows lots of industry going on around a location and also a major freeway here. And so we might have mobile source emissions impacting this location. So we need to think about transport both locally and long distance. There may be something upwind from you, some sort of industrial emission source that has a toxic pollutant, and it may be impacting your community because of the transport conditions around your site. We also want to consider vulnerable populations. I mentioned children. You could also think about elderly, people with, immune system problems, et cetera, so that might be a consideration. And then again, thinking about the proximity of sources to the locations that you're interested in looking at. For JTAP, this is an example. Essentially, the overriding question that this community had was, what is the nature and extent of air toxics transport into tribal communities? So this is the greater Phoenix area, and you can see the Gila River Indian tribal community spans the southern part of the Phoenix area. Then there's Salt River Pima and Fort McDowell, tribal communities up to the northeast. And these communities are, as the population in the Phoenix area has been growing, it's been expanding out towards these tribal communities. And in addition, for the Gila River tribal community, there was a freeway that was going to be, a Highway 10 bypass was going to come right along the northern part of the Gila River community to be able to connect to the 60 here, anyway, to move the freeway south of the downtown area. So this community was very interested to see if what the before concentrations would be before you put in that highway, compared to what they after the highway might be going in. I don't think it's been built yet, but they were worried about what would be going on. So this is a case where just looking at the area and knowing some potential plans, there was some discussion about, what do we need to know before that freeway goes in? Okay. So, oops. Did I get one? Oh, we're good. Oh, sorry. All right. So some examples of the kind of project topic areas that have been being conducted over the last few years are things like other health effects assessments that are going on, and people have designed projects to support those health effects assessments. So, for example, there might be a community study, or a university might be conducting a study to answer a question, let's say looking at asthma incidents, so you might develop a project that builds on that project. So that would be one thing to think about as far as developing a project goal. Another might be that you've been doing some air quality modeling and you want to evaluate your current modeling and you want to do some improvements to it because you know that you may not be modeling some of the pollutants very well. And some of that modeling results might feed into exposure assessments, for example, so that might be another thing that you might be interested in building on. We might want to establish or understand baseline concentrations prior to some change in emissions in the areas. As I mentioned, a new roadway is a typical one where people will look at before and after concentration changes. Or it might be just establishing a concentration and you know that your community is going to be growing or it's going to be putting in another new industry, then you might want to understand what the concentrations are. Or we may not really know what's going on in the area and we might want to characterize the concentrations of specific pollutants that we are worried about, and they may or may not be need for worry but we just don't know and we need to go out and find out. The other thing is we might need to understand what the gradients are in pollutant concentrations. Again, that can feed back into exposure assessments or into modeling to understand better what's happening with concentrations throughout your area. We might want to characterize specific emission sources of concern, and we'll talk about one of these studies looked at pulp and paper mill emissions in their community. We also there's been lots of projects where they were trying to develop new measurement methods and techniques, and that's a frequent community monitoring project topic. And then finally, there's a lot of data that's been collected out there, as Mike and I know, and not a lot of looking at the data. And so sometimes there's been projects that have specifically just said, we've collected a lot of data, but we haven't analyzed it yet. And so we need to go in and look at it and understand it better. So this is just a kind of an overall list. If you look at the most recent community level studies, there's been many different kinds of pollutant sources investigated, and there's a laundry list of them here. And then some of the specific pollutants that have been targeted. And on APTI, under the air toxics section, you'll find final reports from most of these community scale air toxic studies, in addition to their work plans. And so there's a lot of information gleaned from these. There's also a summary report that kind of looked in and went and said what were the lessons learned from some of these studies. And a lot of work that's been going on, sponsored by EPA, to try to understand what are we learning, what do we need to know, what are the what's the next kinds of things that we need to be looking at. All right, I'm going to keep jumping ahead and go into setting project goals. And I've kind of simplified this a little bit from what we did at the workshop, but essentially I just want to talk about some example of goals and then some of the lessons learned. And what I'm realizing is that where we're really going to talk about setting realistic project goals is probably going to come more in the designing the project. So in our next webinar, we're going to have to hang on to the next one, where we're really going to talk about, how do we set realistic expectations with what our how do we set a goal that can meet the resource needs that we have? And I think we're going to talk more about that in the next session, but we're going to touch on it a little bit today.
Can I jump in a little bit, Hillary?
Please do.
So on that previous slide, and I think this is for this entire section, we have it in a linear fashion that you establish a stakeholder group, you assess your issues of concern, and then you set your project goals, and then you design your full project. Well, that may be true in theory. I think a lot of times there's an issue of concern that is brought up by a stakeholder group that you are then trying to set a project goal to meet that thing. But sometimes you may have you can do these things in completely opposite order. They don't necessarily have to happen in this order, but these first 3 or 4 steps all can happen in a number of different orders, and you don't have to establish a stakeholder group. The stakeholder group is already established because they want to shut down that roadway or that project or that facility, and they bring to you the issue of concern. And I think in a lot of cases they're what's driving the actual study, as opposed to you've got an idea of, okay, these are the problems in my community, and I need to go out and find some stakeholders. People, at least in the previous when we were giving this talk, I think a lot of the people, that was the way it was. It was sort of the opposite. Who started the study was the stakeholders, as opposed to you don't have to establish it. They establish themselves, and you just need to get everybody around the table and discuss what's going to happen. So I just want to sort of, well, this is a theoretical process, and in the real world, things happen in a messy way, and so we want to, all these first 4 steps are all iterative and can happen in a number of different orders. That was sort of the point there.
No, that's really good. And in fact, one of the slides coming up will show that those first 4 things is really a loop. That we are, regardless of which one starts first, you're going to have to loop back and forth between those 4 steps, because you're right, it's completely iterative and nonlinear as far as trying to come up with getting to that project design and really, what are our goals? What's the design that meets the goals? Does that address the issues of concern? Is my stakeholder group happy? There's just a lot to balance there. It's not an easy process. It's invigorating and interesting, but not easy. So here's some examples of some of the goals that have been out there that people have been looking at. For example, trying to characterize community or toxic concentrations to help them with the development of risk reduction strategies. So for example, there might be a community that has identified high lead concentrations in their soil, or and they're trying to figure out. Of course, I know we're talking about air here, but they're trying to figure out how to reduce the risk. How did that lead get deposited there? Was it from an airborne, some sort of airborne pollutant, or maybe it was chrome-6? Was it from a chrome plating facility? And so they're really trying to figure out, how do we reduce the risk? How do we characterize where that's coming from? What's the issue? Then another one might be to identify and quantify the impact of a specific emission source on the community. Again, that could come back to something like a chrome plating facility. That just seems to pop up quite often. But it could also be a dry cleaner, or a gasoline station, or a refinery, something big, something small, but a pulp and paper mill. So those are some of the things that we might be looking at. They've also been testing new methods. I think we're not going to touch on that a whole lot. Another one that's used a lot is to obtain ambient measurements to support exposure modeling and emissions inventory and model evaluation efforts. I think that we tend to put, we definitely put a lot of stock in our modeling, but I'm definitely a proponent of ground truthing those models and making sure that measurements that are collected do help support and show some of the problems with those models. Again, the models and the emission inventories are only as good as the information that's given to them, and ambient data provide a very good mechanism with which to compare to those and ensure that we're in the right direction, that things compare relatively well. Because models are great because we can look at what-if scenarios. What if we reduce the emissions of this particular source or this source sector? How will that affect our ambient air? To do those what-if scenarios properly, we need to make sure that we're getting the right answers now with the data that we've collected. And then again, we talked about establishing baseline concentrations for future studies. So for example, where the Gila River population and tribal population wanted to understand the potential impact in the future of a roadway right on their property, they needed to know what the concentrations were prior to that highway being built. So getting back to JTAP, some of their goals were to establish, determine the most important contributors to risk from air toxics, at least from the list that they were going to be measuring, because again, we weren't going to look at all 188 pollutants. We needed to come up with a reasonable list of air toxics of potential concern based on the emissions inventories of the area and the kinds of sources that were in the area. And then try to pin down the likely sources of those air toxics in the study area, and then assess how those concentrations compared to concentrations in other areas of the country, and also to the Arizona's health benchmarks and then national benchmarks. And we were focusing on cancer benchmarks in that case. For Michigan, there was a little bit different approach on their community study. Essentially, they wanted to look at, they'd collected a lot of data. They had a lot of studies going on in Detroit, and they wanted to pull all that information together and create this comprehensive and well-quality assured database to look at supporting additional or more comprehensive data analysis projects. They wanted to place some of their more recent air toxics measurements into perspective, both looking backwards and also looking nationally. And they wanted to try to quantify the impact, the loss of sources or emissions, or loss of sources. They had a lot of things shut down, steel mills shut down, other things from the economy, and they were also targeted emissions reductions, and they wanted to see how the ambient air concentrations were changing in response to those actions. And some of those were based on the economy, some were based on regulations, and so that was really, really interesting for them to try to see what was happening. Was there a response in the atmosphere? They also wanted to look at how risk levels had changed in the Detroit area compared to another part of the state, and then understand comparability and certainty in source apportionment model results, because there have been a lot of source apportionment studies. Again, they want to bring those all together and see what was going on. And then they needed to come up with a plan to effectively communicate the findings that they had and figure out what the next actions would be. So it's a pretty comprehensive study, mainly data analysis focused. And then the Nez Perce tribe had a different kind of project where they said, we want to characterize air toxic concentrations in Lewiston, specifically trying to figure out what the emissions are from the pulp and paper mill that was affecting the community, and then look at the different volatile organic compounds, spatial patterns, and gradient profiles to try to see, again, tie back to how is that pulp and paper mill affecting the community. And I don't know how many of you have lived around a pulp and paper mill. I certainly grew up near one, and they are not very fragrant, or they are very fragrant in a not pleasant way. All right, so once we've gone and set some initial goals, what do we need to do next? Once we have those goals, we have to think about what can we actually accomplish given the study realities. And this is where we were talking earlier about that this process is going to be iterative. You're going to have to revisit your initial goals with your stakeholder group, because I can guarantee you probably will never have enough money to do everything that you want to do, enough resources, enough people, enough expertise, enough time. And so that's going to be one of the key things that you're going to be working on. And the thing might be that you might have to reduce the number of pollutants that you're looking at. You might need to monitor at fewer locations or for a shorter time period. And again, we'll talk about that when we talk about monitoring strategy. But this is that case where we really need to be iterative and really think, go back and forth with what's really important and really drill down into being able to answer what can we actually answer. So that kind of leads to this expectations versus reality, that when, what we've learned out there from the workshop was that folks found that they needed to really be specific in setting their project goals. The more specific they were, the less misunderstandings and problems with expectations occurred. They needed, again, that ties with the second one, goals should not be too broad. So that was the same thing here. And then it was emphasized over and over again, it's hard to meet everyone's expectations. And so that was why it was really important to manage those expectations from the beginning. I was involved in a study, for example, where one of the stakeholders felt that we were going to help design a new monitoring network for an area that had not had monitoring before. And one of the folks in the stakeholder group felt that he wanted to see a new monitor every square kilometer in this area, because he didn't understand sort of the spatial variability of the pollutants of interest in that area. So there was a case where we needed to do some education, some training and sort of what the realities were as far as how air moves and how air mixes, and try to get him to understand that that was not going to be necessary, nor would it be practical. And so, that was just a case where it was an interesting stakeholder group meeting, and hopefully we finally got him somewhat convinced that he didn't need something every square kilometer. This is a new slide from the original. Again, we went back and looked at some of what we heard in the workshop, and these are three comments that we got that I thought were really useful. One was, watch how large a project is. It's always more work than you envision. So again, keeping these really specific was better than trying to take on too much. Do one or two things really well instead of a whole bunch of things not so well. And we heard that a few times. Working with collaborators can be tricky. I talked about trying to limit the size of your stakeholder group and the people that you're collaborating with. because with too many people, you can get too many, especially too many strong opinions in the room. You can be kind of pushed in too many different ways at once. And I think that comes back to also having a very strong leader for your stakeholder group, for your project. You have to have somebody who can really make decisions and, you know, be compromised and everything, but still be in the lead of that group. I think that's going to be really important. And then finally, there was a nice comment to EPA basically saying that these community scale grants were a good way to get software and training in tight budget climate. Okay, so one thing you could do is you can build in some of the tools or training that you wanted to use as part of a community grant. That was something that was allowed, at least in one of the previous go-arounds. And so that was something that one of these stakeholders felt was really useful. With that, that is all I had for today. We ended up going through the first two sections with it, and we're going to come up with more polls for the next time, because I think that was a really fun thing for us to use, and it really certainly helped us. And I think getting to the setting realistic goals, we're going to be working on that more on the next session when we talk about how to set up your monitoring strategy to try to reach those goals. And the other thing is, I think what I didn't start out with this time was, we talked about at the workshop, is that any one of these topics we could probably do you know, a whole day on, but we're trying to at least establish a thought process, get you thinking about some of these things, and then hopefully there might be additional research that could be done in each of these areas to give you more ideas. And it also kind of gives you some of the buzzwords so you can go out and look for some of the material as well. Mike, did you have anything to add for today? I don't see any questions, by the way, so hopefully people are...
I think if you have any suggestions for improving the webinar process, it's difficult for us to find out what your needs are unless we hear or see what's going on. And the webinar format is intrinsically more difficult than an in-person meeting. So please, you know, if you don't want to chat or type a question online, you know, email Barbara or email us after the webinar is over, and we can try to help you individually. It doesn't have to be within the webinar format. It's oftentimes more difficult to talk that way. So.
Right. I missed the hands showing in the audience saying, hey, you know, can you talk more about that? So we do like the interaction. I think you can tell Mike and I both like having that interaction. So this is a little difficult, and we do appreciate people sending us questions. If you'd like to send us questions in advance, that would be helpful as well. But I do promise we'll come up with some more polls for the next time. And I think today we'll end a little early, but I don't think we'll be ending early on the next couple because we have a lot more to cover. This was sort of the introduction from today.
So I do see one hand.
One thing you might, when you go out of the webinar, there'll be a survey.
Okay.
If you could fill that out, that'd really appreciate it. And one of the boxes in the survey is comments. So if you have any questions or any comments on how we can improve things, that would be really appreciated to let us know that.
Yeah, that'll be really helpful to us. Mike, Mike McCarthy, did you have something else?
It seems that Shireen Ali has had her hand raised for 23 minutes.
Except for we can't hear them.
Oh, if we unmute, we'll be able to hear. She's going to the questions pane. All right. So.
Just try to unmute Shireen if she wants to. I don't know if she has a microphone or not.
Oh, good. So I haven't heard, Shireen looks like she started something, but one of the folks said, please make sure to send out a reminder or remind you that you'll get the webinar link the day before. Is that correct, Mike? Is that key, right?
Well, they should have got it. If they registered for it, they should have gotten a reminder.
Okay, yeah, so you'll get a reminder.
Obviously, if they didn't wait for, if they didn't register, well, it's not going to know to send them a reminder. But if you register ahead of time, it'll send you a reminder, I believe, a day ahead of time.
I think one of the issues was if you signed up more than a month ago, some of the systems don't retain your email for that long. And so there was some concerns, like, I forgot how to sign in. But it looks like everybody got the reminders. So we had a good turnout today. All right, with that, looks like we took care of the question, and we look forward to your comments, and we'll see you again in a week. Oh, so, sorry, one more question. How can we get the material in this presentation? I sent material out to the people that had signed up, but it's also available on the web. Let me go back to the first presentation, and I will put it up here. Hang with me for a second.
I have the website right here. It was the first question answered. It's at www.epa.gov, TTN-AMTA-I1, the Air Toxic Data Analysis Workshop 2011.html. So that's it. I don't know if you can see the answers. I think I sent it to everybody.
Yes, and if you just go to AMTIC on the TTN, so if you go to AMTIC and go to the air toxic section, you will be able to get to it. I promise you. So with that, I'm going to close up and thank everybody for being here and being good sports, and we will surprise you with some more polls next time. Thank you, everybody.